Okay, we get a little problem just with the screen recording software. Now let's come back. Okay, let's come back. So find the volume of the solid obtained by rotating this region bounded by 2x squared minus x cubed and y equal to 0. Rotating this region about the y-axis. So let's show the region. Okay, let's show the region. So that is actually the question we ask at the very beginning. So this curve shows the function 2x squared minus x cubed, right? And we understand we cannot use the washer method or disk method to solve it because it will be difficult to work out the inner and outer radius. So we will try the cylindrical shell method. So this curve is 2x squared minus x cubed and y equals 0. That is the horizontal axis. So this region, right? This region rotate about y-axis. So this notation, rotating notation, it denotes the how we rotate this region. So for each rectangle, okay, for each approximating rectangle in this region, when the rectangle rotate about the y-axis, a cylindrical shell is obtained, right? A cylindrical shell is obtained. So we need to figure out according to the formula, right? According to the formula, using the cylindrical shell method, so the volume will be A to B fx, 2 pi x, right? 2 pi x denotes the circumference. 2 pi x fx thickness dx, right? So we need to figure out each part, okay? Each part. So, and we also understand this 2 pi x is the circumference, right? Circumference of the base circle, and fx gives the height of the cylinder, right? Of the cylindrical shell. So here we understand for this rectangle in the blue color, if we rotate this approximating rectangle about the y-axis, this shell in the orange color is obtained, then it will be obvious to check, okay, double check. So the radius you can have xi minus 1, right, inner radius. Outer radius can be xi, right? Let me write it much more clear, okay? So rotate, for example, if we rotate the eyes approximating rectangle about the y-axis. The ice cylindrical shell is obtained, right? Try to take note, okay? Try to take note. Maybe next week I'm going to check your note, okay? I'm going to check all your notes from the first week. The ice cylindrical shell is obtained. We can take this one, okay? We can take this one as the ice rectangle, okay? Ice rectangle. So in the ice subinterval, which is xi minus 1 to xi, then the middle point, right? The middle point, following the formula we established before, the middle point will be the average, right? Will be the average. And you will notice that you will notice that actually here for this shell, the xi minus 1 gives the inner radius, xi gives the outer radius. So the average, okay, the average of those two is the xi bar that can also take as the one radius, right? That is the radius r in our previous formula. So the circumference will be 2 pi xi bar, right? Circumference part will be 2 pi xi bar. And then how about the height? How about the height? So the height for the ice shell, so you will notice that actually this function value gives the height, right? So evaluated at xi bar, right? At xi bar, so will be 2 xi bar square minus xi bar cube, right? Xi bar cube. So we figure out the radius, so we can get the circumference 2 pi xi bar, and then the height is fxi bar. This is to denote for the ice shell, right? Ice shell, actually we can obtain the volume for the ice shell. The volume for the ice shell is Vi equals 2 pi xi bar times f and times the delta x, of course. Delta x, there is no problem. Delta x is b minus a over n, right? Like that. Why we need to work out the formula for the ice shell? Because we need to double check the circumference expression is 2 pi x and the height gives the fx. If the circumference are not those formula, we will change, okay? We will change. So that is the volume for the ice shell, right? For the ice shell. So we understand the total volume. The total volume is the limit of the Riemann sum of the Vi, right? Of the Vi. And in this way, we can understand that the volume should be the definite integral. A and B, it's based on the region, okay? Based on the region from 0 to 2, right? From 0 to 2. And this curve is given, okay? This curve is given in the question. So we know it's directly from 0 to 2. 2 pi x fx dx. My fx is the 2x squared minus x cubed, right? Now let's check the how we evaluate the definite integral. So will be 2 pi x times fx gives the height, right? So you just move the 2 pi as a constant outside. It's a polynomial about x. Then work out the antiderivative. So according to FTC part 2, evaluate the antiderivative at the two endpoints, then take the difference. And this is how the solid looks like, okay? How the solid looks like. And we know this curve, okay? This curve, the solid is bounded by this curve. This curve is 2x squared minus x cubed. And looks like mushroom, not mushroom. Do you think it looks like a mushroom? Some kind of mushroom, maybe. Okay, just try to think about it. Okay, try to imagine how the solid looks like. So the final answer will be 16 over 5 pi gives the volume of this solid. Okay, we just follow the formula. Basically, it will be more general to follow this formula instead of the 2 pi x. fx in that way. Circumference, okay, it's better to follow this formula. The volume of the solid using the cylindrical shells method. Circumference times the height times the thickness. And so far we understand the circumference gives 2 pi x, the height gives the function, and the thickness denotes the dx term in the definite integral. But in some case maybe the circumference is not 2 pi x, or the height is not fx directly. So we should check carefully. Okay, we should check carefully. Let's look at this one, okay? This is more complicated. Find the volume of the solid obtained by rotating about the y-axis, the region between y equals x and y equals x squared. Y equals x squared and y equals x, and we have already know this region in the previous examples, right? And we know those two curves are intersected at 1, 1 and 0, 0. So this region, right? This region. And we have already discussed one example before when they rotate about x-axis, okay? When they rotate about x-axis, it looks like this way. Right? When they rotate about the x-axis, this region, and we evaluate the volume, right? We evaluate the volume using the washer method. So here is one, right? So this is the case when we rotate about the x-axis, we obtain this solid. Now this question changes into rotate the region about the y-axis. So here, rotate this region about the y-axis. This blue color is the region, okay? This blue color is the region. Rotate about the y-axis, it looks like this one, okay? I will call it looks like a bow, okay? Looks like a bow. And the inside is kind of empty, right? Looks like a bow. And then for this one, okay, we are going to use the shell method. We are going to use the shell method. So now let's check this region first. Let's check the region, and we know it's from 0 to 1, right? Let's check this region. This is the straight line. This is a parabola, right? This is a parabola. And we will do the same thing, right? We will do the same thing to check that. So the ice rectangle, we will take this one as the ice rectangle, okay? Ice rectangle. So the ice rectangle is rotated. So for this region, right? The ice approximating rectangle, right? Approximating rectangle is rotated about the y-axis. And the ice shell, it's shelled, right? The ice shell, cylindrical shell. The ice shell is obtained. Now let's figure out, okay? Now let's figure out in the ice subinterval, okay? In the ice subinterval. So the radius, okay? Let's check the radius for this shell. as I told you, it's not always 2 pi x of the circumference. Okay, so you will check that for the left end point xi minus 1, that will be the inner radius here. Okay, and then the outer radius will be xi here, this endpoint, the right end point of the rectangle. So the xi bar will be the average, right? The xi bar, we take the xi bar as the r, as the radius, right? We understand this r notation, which is the average of the inner and outer radius, which is the inner and outer radius, right? We still got xi bar in this way, and we understand if we are going to evaluate the circumference of the base circle, it can be evaluated using 2 pi r again, right? So 2 pi xi bar. And now how about the height? How about the height? So that is the radius, right? The average radius, actually. The average radius is xi bar. And then how about the height? Is the height fx again or not? Check the height. So here the height is not fx, and we have two functions, right? Here actually we have two functions. We have y equals x, we have the y equals x square. So the height, we can check that this is the height in the purple color. This is the height of the rectangle. How can we get this height? Actually, this height is between the two curves, between y equals x and y equals x squared. So the shell's height, okay, the height for the ice shell would be x minus x squared, will be the difference of those two curves. So that's why we note in this way. Okay, we note in this way. So we will write the height for the ice shell. The height, change the color. The height for the ice shell is not fx, again will be the difference. So with the middle point, okay, with the middle point, now this height fxi will be a new one, okay, will be a new one, will be xi bar minus xi bar square, right? Because the height, we still understand the rectangle's height is evaluated. The height is the function evaluated at the middle point, okay, middle point. So here we understand the ice shell volume, okay, the ice shell's volume will be 2 pi xi bar, the radius times the height. Now what is my height? My height is not only one function, will be the difference of the two functions, right? So will be xi bar. How can we write this function according to here? Xi minus x square, but especially we evaluated, what we call is we evaluated at xi bar, okay, at xi bar, so the height will be xi bar minus xi bar square. So fx, to circumference height, then times delta x. What is my delta x? My delta x is the term b minus a over n. What is b? B should be 1, right? It's from 0 to 1, like that, okay, like that. So the volume, right? The volume, again, the volume for the shell can be rewrite as the limit of the Riemann sum and vi, right? Vi. Now, what is my fx here? So we should be careful, okay? This region is bounded by two function curve, y equals x and y equals x squared. So the definite integral starting from 0 to 1. How can you get starting from 0 to 1? How can you obtain the lower and upper limit? According here, right? Follow the region here. Follow the region here. From 0 to 1, 2 pi x, right? 2 pi x. So here, all those, this is just for the ice shell. So in the definite integral, that becomes the x, right? And then the function fx, this is the function fx. So we will write x minus x squared. And then dx term works or equivalent as the differential term dx. Delta x is equivalent as dx. Now evaluate this definite integral, right? So let's check the solution, right? Let's check the solution. The region and the typical shape are shown in figure. We see that the shell has a radius, okay? So this is the case. I use the xi bar, okay? I use the xi bar in my notation, which is identical with the previous cases we analyzed. But you can also take this one as a radius x, and we know this x is between 0 and 1. Okay, if you take it as x, that will be much easier, or that will be more close to form the definite integral. But I use the middle point in the ice subinterval just let you understand how we starting from the ice, starting from the volume for the ice shell. Okay, so if you use the x notation, so you have the shell radius is x, okay, x, and then the conference will be 2 pi x, and so the height will be x minus x squared. Okay, then it's the same, the volume formed in this way. You move 2 pi outside, then it's a expression, it's a polynomial about x squared. Okay, it's a polynomial about x, then you find the antiderivative. Finally, you get the solid. Okay, you get the solid. It's pi over 6. Okay, why it's not just the bottom top curve minus bottom curve? Yeah, it's the top curve. Yeah, you're right. You're right for this question. What we did here, okay? What we did here to take the height fx, okay? Fx actually is the x minus x squared. You can also take this one as the top curve minus the bottom curve. Yeah, it's identical, okay? It's identical with the area between two curves we discussed before, okay? But this function just denotes the height, okay? Just denote the height. We need the volume of the shell, okay? We need the volume of the shell. Yes, it's right. You can take the height of the rectangle as the difference between the two curves. So using x as the variable, you can use top curve minus the bottom curve. You can understand this difference, the height in this way. Okay, so that is example 2. Okay, example 2, and those two are the regions rotating about y-axis, either x or y-axis. We will see one more example. It's rotating about some other lines, okay, some other straight lines rather than the x and the y axis. So this one, okay, this one. Find the volume of the solid obtained by rotating the region bounded by y equals x minus x squared. Let me just show you how we work out step by step. And be patient, okay? Be patient. Let me finish this example, then we will do the quiz, okay? Then we will do the quiz and take a break. So be patient. So find the volume of the solid. Mouse is not working. Find the volume of the solid obtained by rotating the region bounded by the curve. Alright, let's take a break first.